Question 1. Describe what happens when a reaction mixture reflux and why it's necessary for complete oxidation to ethanoic acid. So, a mixture of liquids is heated to boiling point for a prolonged time. Vapor is formed which escapes from the liquid. Mixture is changed back into liquid and returned to the liquid mixture. Any ethanol that initially evaporates can then be oxidized. We're at half equation for overall oxidation of ethanol into ethanoic acids. So we've got ethanol to ethanoic acid. So CH3CH2OH, arrow ethanoic acid CH3COOH. Now we've got 1 carbon, 2 carbons, 1 carbon, 2 carbons, 3, 4, 5, 6 hydrogens, 3, 4 hydrogens on the right hand side. So what we have to do, so we move through 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So we're going to add add a H2O molecule here, and then we also need to add 4 H pluses here, and then for the overall charge to be 0 on the right side, we need to add 4 negatively charged electrons. 1.3 use data to describe how you obtain a sample of ethanol from a mixture of these 3 compounds. We can see ethanol has the lowest boiling point. That's first things first, and that's going to be very useful because first things first, the mixture is heated in a container with still head containing a thermometer let's just say thermometer inside, water cooled condenser connected, and suitable cooled. Collect sample at the boiling point of ethanol. Cooled collection vessel is necessary to reduce evaporation of ethanol. Question 1.4. Well, ethanol. Well, ethanoic acid and ethanol both have hydrogen bonding, that's for sure. So ethanol and ethanoic acid have hydrogen bonding, and the intermolecular forces in ethanol, dipole forces, are weaker than hydrogen bonding. Describe student could use chemical tests to confirm that the liquid contained ethanol and did not contain ethanoic acid. So liquid contained an aldehyde, not carboxylic acid. Tolerance region. Add tolerance region and warm mixture, and what will happen is the results with tolerance region, silver mirror. for aldehyde for ethanol. And this is to confirm. And then to confirm ethanoic acid, to confirm the absence of ethanoic acid, add sodium hydrogen carbonate. Results no effervescence observed, hence no ethanoic acid present. Question 2. Calculate the value of Kc for the reaction of ethanoic acid and ethanol at 20 degrees Celsius, 6 marks. So Kc is equal to square brackets products to the power of P divided by reactants to the power of R. So we've got the products CH3COO, CH, not enough space, CH3COO, CH2, CH3, and H2O divided by CH3COH and CH3CH2OH. And remember, because it's Kc, square brackets. We're given the initial moles of ethanoic acid, initial moles of ethanol, allowed to reach equilibrium, and then we know that ethanoic acid reacts with dark. Okay, so first things first, we're going to find out the moles of acid at equilibrium. So the moles of sodium hydroxide in each titration is 6.40 times by 10 to the power minus 4. I'm not going to be able to do the full calculation because I'm not going to have enough space. And how did you get that? Well, you do 3.20 times by 2.0 times by 10 to the power minus 1 divided by 1000. The moles of sodium hydroxide, concentration and volume. Then we need to find out, well, that's for 10 centimeters cubed, but we want the moles of acid in 250 centimeters cubed, so we need to times by 25. Times that by 25, and we get 1.60 times by 10 to the power minus 2. And the moles of ester and water formed, well, the moles of acid reacted is going to be 8.00 times by 10 to the power minus 2 minus 1.60 times by 10 to the power minus 2, 6.40 times by 10 to the power minus 2. That's the moles of the ester and acid form. We subtract, and therefore moles of ethanol at equilibrium was going to be 1.20 times by 10 to the power minus 1 minus 6.40 times by 10 to the power minus 2, and we get 5.60 times by 10 to the power minus 2, and then we substitute values in. So it's going to be 6.40 times by 10 to the power minus 2 squared, because that's the moles of the moles of that and that, divided by 1.60 times by 10 to the power minus 2 times by 5.60 times by 10 to the power minus 2, and all the moles of concentration and volume, concentration moles divided by volume, but all the volumes will cancel out on one here, and we should get 4.57. Two series significant figures or two decimal place, the appropriate number of significant figures. Complete table 2. We're just subtracting them, so 4.50, 4.00, 4.20, 3.95. Now why would it ask you to do this? Just a simple subtraction. Is because most students, including myself, would fall for the mistake of writing 4 in here, but they all have to be to two decimal places or three significant figures, otherwise you won't get the mark. So calculate mean titer and justify your choice of titers. Mean titer is the one that is within 0.01 centimeters cubed of each other, so it's going to be that and that. So 4.00 plus 3.95 divided by 2, 3.98, and the reason being is because titers 1 and 3 are within 0.1 centimeters cubed, which are the titles 1 and 3 are concordant. Select from table 3 a suitable indicator. Thymol blue. Percentage of uncertainty. Okay, uncertainty mean titer is 0.15. Calculate percentage of uncertainty in this mean titer. Mean titer is 3.98, so it's just going to be that divided by 3.98. We're not timesing by 2 or anything because we've only got one mean titer. We stand by 100 on the percentage, 3.77%. Reduce percentage of uncertainty. Use lower concentration of sodium hydroxide. Of NaOH so that a larger titer is required. Use low concentration of sodium hydroxide so that a large titer is required. Question 3. Consider whether it is essential and justify the answer. Wearing plastic glove to hold the TLC plate. So this is obviously chromatography, TLC chromatography, thin layer chromatography. Okay, so the first thing, 4 marks. Wearing plastic gloves. Is it essential? It is essential to prevent contamination from hands to the plate. Adding solvent to a depth of not more than 1 centimeter. Add developing solvent to depth of not more than 1 centimeter cubed. It is essential. If solvent is too deep, it will dissolve the mixture from the plate. Allow the solvent to rise up to the plate to the top. That's not essential. Reason being is because the RF value can be calculated if the solvent does not reach the top of the plate. Therefore it's necessary. Allow plate to dry in a fume cupboard. Allow plate to dry in a fume cupboard. That is necessary. Reason being, it is essential. Sorry, because solvent is toxic. Outline the steps needed to locate position of amino acids on the TLC plate, thin layer chromatography to determine the RF values. Spray with developing agent / use UV. Measure distance from initial pencil line to the spots. Measure distance from initial pencil line to solvent front line. An RF value, in this case, that, let's just say that's X, that's Y, it's going to be X divided by Y. Explain why different amino acids have different RF values. Well, different amino acids, what they're going to have different polarities. Amino acids have different polarities. Therefore have different retention on the stationary phase. Question 4. Use the concept of electronegativity to justify the acid strength of ethanoic acid and ethanoic acid, ethane dioic acid and ethanoic acid are different. Let's go through the structure of the two acids. the acids are of the form RCOH, they're both carboxylic acids, but in ethanoic acid R equals CH3, ethane dioic acid R equals COH. Stage 2, inductive effect. The unionized COH group contains two very electronegative oxygen atoms. What does that mean? Well, hence has a negative inductive effect, where CH3 group has a positive inductive effect, or electron pushing effect. Stage 3, how polarity of OH affects strength. The OH group in the ethane dioic acid is more polarized, more dissociation into H plus ions. Ethane dioic acid is stronger than ethanoic acid. Calculate a value for the pH of the buffer solution. So first thing we need to do, let's find out the moles of, first thing I can see, moles of sodium hydroxide. Which is already given us in the question. Let's read it. And to find out the moles of ethane dioic acid remaining, well, we have to do 1.00 times by 10 to the power minus 1 minus 6.00 times by 10 to the power minus 2. Once you've done that, the rest of it is going to become dramatically easier, and exponentially easier, because now obviously we're given acid dissociation constant. So Ka is equal to H plus A minus HA, where the square brackets represents the concentrations. Ka, and what we're trying to find, well, we want to find pH, we need H plus ions. H plus, rearrange it, is equal to Ka times by HA divided by A minus. Substitute the values in. I know Ka is 5.89 times by 10 to the power minus 2. I know HA is what, 4.00 times by 10 to the power minus 2 divided, that's the moles though, so the concentration is moles divided by the volume, so divided by V. And also A minus is 6.00 times by 10 to the power minus 2, the OH minus A minus here, divided by volume. Obviously the volumes cancel out, and we're left with 3.927 times by 10 to the power minus 2. And that is the concentration of H plus ions. And therefore pH minus log 10 H plus pH is equal to, substitute that into there. You should calculate a 1.406, but we want to do 2 decimal places because it's pH, 1.41 to 2 decimal places. Introduce the equation where the reaction occurs and use to calculate original concentration of ethane dioic acid. So we've got 5 H2C2O4 plus 6 H plus 2 MnO4 minus, arrow should be here but not enough space, so here 2 Mn2 plus 10 CO2 plus 8 H2O. Obviously the arrow definitely should be here, not there, but in the exam you probably have enough space. Since my drawing it is a lot larger, I can't really do it there. 5H2C2O4 plus 6H plus 2MnO4 minus ROM2Mn2 plus 10CO2 plus AH12. And then calculate original concentration of that. So we need to find out the moles of KMnO4, which is what? 20.2 times by 2.0 times by 10 to the power minus 2 divided by 1000. 20.2 divided by 1000 converted to moles per dm minus cubed times by 2.00 times by 10 to the power minus 2. That will give me 4.04 times by 10 to the power minus 4. Now for the moles of H2C2, well, we need to times that 5 over 2. I get 1.01 times by 10 to the power minus 3. Concentration moles divided by volume, moles concentration volume, concentration moles divided by volume is going to be, it is going to be 1.01 times by 10 to the power minus 3 times by 1000 divided by 25, or you can do the division, and that will give me 4.04 times by 10 to the power minus 2. Is it the correct units? Yes, moles per dm minus cubed. Identify the species responsible for the two peaks. It's going to be CH3OCOCOOH, positively charged, and CH3OCOCOCH3 square brackets positively charged. Identify, outline how the time of flight mass spectrometer is able to separate these two species to give two peaks. Time of flight mass spectrometer, so what is it? Acceleration, ionization, the ion drift and detection, I think. But yeah, it's just representing that. So the positive ions are accelerated not by a kinetic field, by an electric field. So they all have the same kinetic energy. The positive ions with MZ value 104 have the same kinetic energy as the ions with M/Z 108 and move faster, hence the ions with MZ equals 104 arrives at detector first, and then definitely can separate two species because you know the first one is the MZ value with the 104. And that's the end of the past paper questions.